So we're talking about MGF and moments of Bernoulli distribution. So we'll be continuing with that. So we had observed all the raw moments about origin are equal to P. So the first four moments about origin are mu1 dash, mu2 dash, mu3 dash, and mu4 dash, which are equal to P. And we were evaluating mu4, beta 2, and gamma 2. Mu4 is the formula given by the mu4 dash minus 4 mu3 dash mu1 dash 6 mu2 dash mu1 dash square minus 3 mu1 dash power 4. Now every raw moment is P here. So when you substitute that, you will observe that mu4 is equal to P minus 4P square plus 6PQ minus 3P power 4. So when you take P outside as common, you'll be left with this. And if you factorize that, you will observe that 1 minus 4P plus 6P square minus 3P power 3 is equal to 1 minus P into this. So I can write this as P into 1 minus P into this term. And 1 minus P is equal to Q. So I can write mu4 finally as PQ into 3P square minus 3P plus 1. So you could further factorize that also by taking 3P common, you get 1 plus Q, 1 minus P there. Okay, so we have mu2. Mu2 is equal to mu4 by mu2 square. So we have just observed mu2. As said, mu2 could be further simplified. So this step was missing, so just replace it. So you can take minus 3P or 3P outside. So if you do that in the first two terms, you will be left with P minus 1 or minus P plus 1. And then you have plus 1. So this 1 minus P can be written as Q. So you can write this as 1 minus 3PQ. Fine. So that is our mu4. So if I use that, I can have the value of mu4 as 1 minus 3PQ divided by PQ. So this is the simplified form of mu4. ಮತ್ತೆ ಹೊಸದಾಗಿ ಬರ್ಕೊಳ್ಳೋದು ಬೇಡ. ಲಾಸ್ಟ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ mu4 ಎಲ್ಲ ಡಿರೈವ್ ಮಾಡಿದೀವಿ. ಅಲ್ಲಿ ಇಲ್ಲಿವರೆಗೂ ಆಗಿತ್ತು. ಇನ್ನೊಂದು ಎರಡು ಸ್ಟೆಪ್ ಅದನ್ನ ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿ ಬರ್ಕೊಳ್ಳಿ. So what we did is we just took this 3P common and we observed that it could be simplified as 1 minus P. So I can write that as 1 minus 3P. Now coming to the calculation of gamma 2. Gamma 2 is beta 2 minus 3. So this will be 1 minus 3PQ divided by PQ, which is our beta 2 minus 3. So when I simplify this, I get 1 minus 6PQ divided by PQ. So LCM tagondaga 3PQ agutte, minus 3PQ minus 3PQ becomes 1 minus 6PQ. So gamma 2 is equal to 1 minus 6PQ, or you could write that as 1 by PQ minus 6. Now coming to the interpretations of gamma 2. So you can say the kurtosis will be greater than 0 if your 1 by PQ is equal to 6. If it is less than 1 by 6, more than 1 by 6, you will have respectively Latic-Curtic and Leptokurtic distributions. So gamma 2 greater than 0 implies 1 by PQ minus 6 greater than 0, or 1 by PQ greater than 6. ಅಲ್ಲಿ ಕೊನೆಯದಾಗಿ ಪ್ರಾಪರ್ಟೀಸ್ ಬರ್ಸುವಾಗ kurtosis property I just use 1 by P. If 1 by P is greater than 6, then we understood that it is equal to a leptokurtic distribution. It's not just 1 by 6, you replace that by 1 by PQ greater than 6. And but generally P greater than 1 by 6 when we had leptokurtic distribution at the bus. So this 1 by PQ greater than 6 implies that PQ is less than 1 by 6. So only new P less than 1 by 6, it is leptokurtic and the barkondri. Replace that by PQ less than 1 by 6. Now similarly, if PQ is equal to 1 by 6, then the distribution is almost mesokurtic. If PQ is greater than 1 by 6, then it is platycardic. So this is the interpretation. So just by looking into the value of P, you can say what type of kurtosis we observe. Barcode correction ಮಾಡ್ಕೊಳ್ಳಿ. So we have PQ less than 1 by 6, PQ equal to 1 by 6, or PQ greater than 1 by 6. Alternatively, we'll have leptokurtic, mesokurtic, and platykurtic distributions. Okay, so this is about the moments, raw and central moments from the for the Bernoulli distribution. Now we also know the definition of arc central moment. Arc central moment is nothing but expectation of x minus expectation of x to the power of r. So if you remember, our mu r is given by summation x minus x bar to the power of r divided by n. So I can write the central moment using the formula mu r is equal to expectation of x minus expectation of x to the power r. So this is other way to obtain the central moments directly. Now since we have very less values for x, actually only 2 values taken by the Bernoulli variable, you can derive your mu1, mu2, mu3, mu4 directly using the formula of the central moment other than using the raw moments. So one of the method what we usually do is we compute mu1 dash, mu2 dash, mu3 dash, mu4 dash, and using this we will compute the central moments. That we do when we have larger values of x as well as the probabilities, because every time taking x minus x bar to the power of r when you have several values of x becomes a tedious job. So that's why we used to obtain the central moments from the moments about origin. But whenever you have special distributions like Bernoulli 2-point or a degenerate distributions, you can easily obtain the moments using the formula. So I'll have mu1 is equal to expectation of x minus expectation of x to the power of 1. And this is nothing but your total of x minus x bar. And when you simplify this, you will get e of x minus e of x. E of x is again e of x. So the first moment automatically comes to 0. Now similarly, when you look into the second moment, it is e of x minus e of x whole square. Now, since we already know e of x and e of x square of Bernoulli, we can compute it directly, or we could use the definition also. So we know that any expectation to the power of r for a Bernoulli distribution is equal to p. So what we can do is we can use that and we could simplify it, or since we know that it is variance, you can write it as PQ directly, or if you don't know, just expand this. You will have expectation of a minus b whole square, a square minus 2ab plus b square. Now send your e inside, so you get e of x square minus 2 e of x into e of x plus x square. So it is actually expectation of x into this, and e of x is a constant, so you can take it outside e of x, so it becomes e of x into e of x, which is e of x whole square, and again you will have e of x square. So this becomes p minus 2p square plus p square. So you have p minus p square, which is p into 1 minus p, which is pq. So this is the other method of obtaining the variance directly using the definition of mu. Okay, now similarly, you can obtain mu3 as well as mu4 just by using e of x minus e power x whole cube. So just take a minus b whole cube, expand it, simplify, put e of x square, e of x cube as p, and you can simplify it. Now, the more general way of deriving this moment is by using the definition of rth moment. Now, any mu r is given by e of x into x minus e of expectation of x minus e of x whole to the power of r, and we know the definition of expectation. Expectation of any function is summation of the product g of x with p of x with all possible values of x. So by using these two definitions, now I can derive a more general formula for mu r itself. So according to this, expectation now is replaced by summation sign, summation of x belonging to x, and in place of g of x, I have x minus e of x to the power of r, so this into p of x. So if you remember the Pmf of Bernoulli, it is p to the power of x, 1 minus p to the power of 1 minus x, with x taking only two values, 0 and 1. So the mu r just simply becomes summation of x equals 0 to 1. You have x minus e of x to the power of r into p to the power of x, 1 minus p to the power of 1 minus x. Now substitute x is equal to 1 first, 0. So we'll have 0 minus e of x, and we have e of x is equal to p. So this will be 0 minus p to the power of r into p power 0, 1 minus p power 1 minus 0. And when you put x is equal to 1, you get 1 minus p to the power of r, p to the power of 1, 1 minus p to the power of 1 minus 1, which simplifies to minus p power r. So minus p whole power r, and this becomes 1. So I'll have 1 minus p plus 1 minus p to the power of r into p. So this is the rth central moment of the Bernoulli distribution. Minus p whole power r, 1 minus p plus 1 minus p whole power r into p. Now, in the final formula, you can substitute r is equal to 1, 2, 3, 4 and generate mu1, mu2, mu3, mu4, as well as you can obtain beta 1, beta 2, gamma 1 and gamma 2. So several ways of obtaining the Carpiasson's beta and gamma coefficients are there. Look into the question, accordingly answer. So if they ask, just comment on the skewness and kurtosis. You could actually start with the derivation of center moments directly, because this is easier rather than computing mu1 dash, mu2 dash, mu3 dash, mu4 dash, and then generating these values. So I'll give you the values for the first four moments using this expression. So remember this, mu r for Bernoulli is minus p to the power of r into 1 minus p plus 1 minus p to the power of r into p. So taking r is equal to 1, we have mu1 is equal to minus p power 1, 1 minus p plus 1 minus p power 1 into p. So we have minus a as well as a. So this gets simplifies to 0. Now taking r is equal to 2, you get mu2, which is minus p power 2, 1 minus p plus 1 minus p square to the power of p. So this is minus p whole square, which is p square into q, plus 1 minus p is q square into p. So this will be pq into p plus q. We know that p plus q is equal to 1. So we have mu2 is equal to p. Now similarly take r is equal to 3, r is equal to 4, and you can obtain your mu3 as well as mu4. So mu3 will be minus p power 3, 1 minus p plus 1 minus p power 3 into p. So simplify that, and mu4 will be minus p power 4 into 1 minus p plus 1 minus p power 4 into p. So this is how you can easily derive your mu1, mu2, mu3, mu4. So This serves an easier and simpler way to talk about the central moments as well as the uh, beta and gamma coefficients. And in the last class, we also saw we could obtain it from the MGF also, mx of t for a Bernoulli distribution is given by q plus p e power t. Now we can differentiate it and then we can generate the moments. Now for a Bernoulli distribution, we could also talk about mean deviation from mean. So generally we say mean deviation from mean md x bar is equal to summation mod x minus x bar divided by n. So in terms of expectations, we could write md e of x. This will be expectation of mod of x minus expectation of x, which could be written as expectation of mod of x minus p when it comes to Bernoulli, because for Bernoulli, e of x, which is mean, is equal to p. And definition of expectation is total of g of x into p of x. So this will be summation x equals 0 to 1 mod x minus p into p of x. So directly write p of x, which is p power x, 1 minus p to the power of 1 minus x. So now put x is equal to 0 and 1 and simplify this. So when you put x is equal to 0, you get mod of 0 minus p into p to the power of 0, 1 minus p to the power of 1 minus 0, plus when you put x is equal to 1, you get mod of 1 minus p to the power of 1, 1 minus p to the power of 1 minus 1. So you have mod minus p into 1 minus p plus mod 1 minus p into p. I can further simplify that also. We have p as a positive real number. Your p always lies with 0 to 1. So any mod minus p automatically implies it is p itself. And also if you look into the value of 1 minus p, 1 minus p is also always greater than 0. Therefore, mod of 1 minus p is also same as 1 minus p. Or you could replace 1 minus p by q. Q is also a positive real number within 0 and 1. So mod of q is same as q. So remember this for Bernoulli, mod p, mod q, they take the same value, p as well as q. So we have our MD E of x, which is obtained as mod minus p into 1 minus p plus mod 1 minus p into p. Now that could be simplified as p into 1 minus p plus 1 minus p into p, which becomes 2 times of pq. So this is the mean deviation of mean for a Bernoulli distribution. 1 minus p is q, so I'll have pq plus pq, which is equal to 2pq. Now, so almost all the results are derived. I have given you the examples of Bernoulli trial and Bernoulli distribution variable. We'll look into that. Okay, no. Examples of Bernoulli trial and Bernoulli distribution. So a trial is nothing but conduction of experiment and how we can obtain the Bernoulli random variable. A random variable is always indicated by x, and here we are giving examples for the case of Bernoulli distribution. Now you can write the examples of all those experiments where you can generate or divide the sample space into two equal parts. So example, inspecting an item, manufactured item to be defective. So we are inspecting only one item. So from that, I can generate the equivalent variable x as x is equal to number of defective, or you could say non-defective also, number of defective item in the inspection of one item. Inspection of one item. So ಒಂದು ಐಟಮ್ ಇನ್ಸ್ಪೆಕ್ಟ್ ಮಾಡ್ತಿದೀವಿ, ಒಂದೇ ಒಂದು ಐಟಮ್ ಇನ್ಸ್ಪೆಕ್ಟ್ ಮಾಡಿದಾಗ ಅದರಲ್ಲಿ ಎಷ್ಟು ಡಿಫೆಕ್ಟಿವ್ ಸಿಗ್ಬೋದು, ಎಷ್ಟು ಸಿಗ್ಬೋದು, 0 ಡಿಫೆಕ್ಟಿವ್ ಸಿಗ್ಬೋದು ಅಥವಾ ಒಂದು ಡಿಫೆಕ್ಟಿವ್ ಇರಬಹುದು. Therefore x is equal to 0. Similarly, second example could be tossing a coin once. So I can define x as number of heads, or you could also define as number of tails also, number of eggs or tails obtained when a coin is tossed. One way coin toss ಮಾಡ್ತಿರೋದ್ರಿಂದ I could get either 1 head or 0 head. So again x is equal to 0, 1. Similarly, you can say x is equal to giving the birth to a child. Again, we are just looking into the case where we have only one item used, one coin, one item, one particular baby, and so on. So for this, we could define x is equal to number of male children or female children. Other one dashte tagobeko, one particularly, but you can model it for both male and female. X is equal to number of male children observed in a birth. So now giving birth to a child anta helirodrinda, we are not talking about giving birth to simultaneously multiple children like twins adar ಬಗ್ಗೆ ಮಾತಾಡ್ತಿಲ್ಲ. And even if you are talking about happening of birth of twins or twins, birth can happen to one child at a time. So there will be a gap between the happening of the births. So the baby could be either male or female, and if you count how many male or female observed when only one baby is born, that will be x is equal to 0, 1. So this is how you construct the variable as well as the trial. So trial experiment ke example kodi antandre experiments example le kodbeku. So when they ask you give example for random variable, define it as x, and it is always a real number. So you have to define x as number of, and give example. Bernoulli ಕೇಳಿದಾಗೆಲ್ಲ ಬರೀ one item, one object ಮಾತ್ರ example ಕೊಡ್ಬೇಕು. Because if you consider multiple objects, then the values for x could be multiple in number. So that doesn't define a Bernoulli case. Okay, so this is about Bernoulli distribution. So we observed the PMF, we looked into parameters, we derived various formulas for the mean, variance, and the deviation. We looked into raw moments, central moments, as well as beta gamma coefficients, and we looked into MGF. So MGF, you have to remember. Now till now, I think you have observed 2 MGF for Bernoulli. it is q plus p e power t, and in the other class you have observed for uniform distribution, right? So you had continuous uniform distribution, and you had the mgf there as e power a e power dt minus e power at divided by e into b minus a. So ಎಲ್ಲ distribution pmf by heart ಮಾಡ್ತಾ ಇರಿ, mean formula by heart ಮಾಡ್ಕೊಳ್ಳಿ, variance by heart ಮಾಡ್ಕೊಳ್ಳಿ, mgf by heart ಮಾಡ್ಕೊಳ್ಳಿ. Now, so we'll continue with this. So next is generation of the binomial distribution. So before that, I will look into a special case where the Bernoulli is derived. So that is called as a 2-point distribution. Bernoulli is a special case of 2-point distribution. So what is this 2-point distribution? A 2-point distribution is a distribution where your x is generally taking two values, say x1 and x2, with certain probabilities, say p of x. So if I say x1 is taking probability k, then x2 will be taking probability 1 minus k, so that the total of probability is equal to 1. So such a distribution is called as 2-point distribution. In a 2-point distribution, if I take x1 is equal to 0 and x2 is equal to 1, and if I take, say, k is equal to q, then this generates Bernoulli distribution. So we could say Bernoulli distribution is a special case of 2-point distribution. What's a 2-point distribution? A distribution where the random variable is taking only two values with probability such that total probability is equal to 1. Now, how to write it in terms of mathematical form or the PMF? We could write P of x is equal to x1 is equal to 1 minus P of x is equal to x. So this is the alternative way of writing the PMF. And for various values of x1 and x2, you could generate other distributions. So when you look into the mean of this distribution, E of x given by the formula summation x into px over x taking different values. So I'll get the first value of x1 is x into k plus x2 into 1 minus k. So until and unless you know the value of your x1, x2 and k, particular formulas cannot be given. So we have to just use the definition in obtaining mean and variance. So similar example could be given. So I could have x1 is equal to, say, 2, x2 is equal to 3, and maybe k is equal to 0.1. Then I get the distribution as, say, 2, 3 with probability is 0.1 as well as 0.9. Now, another special case of this point distribution, 2-point distribution, is if k is equal to 0.5. So if k becomes 0.5, 1 minus k is also 0.5. So the probabilities are constant. So you can write the PMF as p of x is equal to xi is equal to k. So in this case, you will have p of x is equal to x1 is equal to p of x is equal to x2. So that is the PMF of this particular case. Now similarly, you can talk about a case where your x is taking only one value, and when x takes only one particular value, we simply we can't call it as a random variable, we call it as a degenerate random variable. The concept of variable comes into picture when it is taking multiple values, but we have the case where I have only one value being taken, then we call that as a degenerate variable. So mathematically, I could say x is a variable which takes some real numbers. So when I say some real numbers, it could take one value, two value, three value, and so on. So we have started discussing about the case where our x is taking two values. Now similarly, I could have a distribution where x is taking only one value, and that is called as a degenerate random variable. Degenerate random variable. So if I say x is degenerate at say x1, it simply means p of x is equal to x1 is equal to 1. That is, my random variable is taking only one value with probability exactly equal to 1, and the other case are equal to 0. So you could write Pmf alternatively as p of x is equal to x1 is equal to 1 and 0. So this is only if x is taking x1 and is not taking other values. So p of x is equal to x equals 1 if x equals that particular value, and so on. Now the mean of this particular distribution remains the value itself. So when you apply the formula, E of x is equal to x into px. So when you generate x into px, you'll observe only x1. So mean of this is equal to x1. And if you look into the variance of a degenerate random variable is always equal to 0. So therefore, E of x is equal to x1. For a degenerate random variable, the mean is same as the value taken by the random variable, and variance of x is equal to 0. So try and derive the variance and observe that it is equal to 0. So this is about degenerate. I could have various cases when x1 is not in. You look at it, if they say x is degenerate, right? X is degenerate. Degenerate meaning ಅಂದ್ರೆ ನಿಮ್ಮ x generate ಆಗ್ತಿಲ್ಲ ಅನ್ನೋ ತರ ಅರ್ಥ. ಯಾಕೆಂತಂದ್ರೆ it is taking only one particular value. So if I say x is degenerate at k, that means that my x is actually taking only one value k. This implies x is equal to k with probability 1. So either you write it as x1 or k or p or any other number. This is the definition of the degenerate random variable. So we define random variable as a function from sample space to real number, and we could now also define functions of the random variable itself. So if I have x as a random variable, I have x a random variable. So if x is an RV, then we have f of x is also an RV. So this is what we will be proving in your higher studies. For time being, we'll just use the result and we'll see how to generate various random variables using the simple random variable x. And we'll be looking into only the special cases of that. So the first case is the sum of independent and identical Bernoulli case. So we started the discussion with Bernoulli. So we'll talk about sum of independent and identical distribution or the variable. And in this case, we'll start with Bernoulli variable. We are taking the function to be sum of what variables? Sum of independent and identical Bernoulli variables. So what is independence here? So we are having the statistical independence. Definition of independence: if you have two random variables or bivariate random variable where x is taking the value x, y is taking the value 1, if you could express the joint PDF as the product of marginals, then we could say the variables are independent. So when we talk in terms of trials or events, if I have two events A and B, so if I have two events A and B, if A and B are independent, then we say P of A intersection B is equal to P of A into P of B. What's the definition of independent events? The events which happen such that happening of one doesn't influence or get influenced by the happening of other event. So if you're talking about multiple events, happening of one should not affect the happening of other. In that case, we call them as independent variable. And then here we are talking about independent Bernoulli variable or independent Bernoulli trials. And then we are talking about identical. Identical in the sense they have the same distribution and also distributional properties. And only one property which we observe in Bernoulli is the parameter P. So if you know the value of P, you can write the PMF, mean, variance, standard deviation, mean deviation, all your moments, beta coefficients, gamma coefficients, MGF. Everything is based on the value of P. So as P changes, these values for a particular distribution changes. So we say if we are talking about several such Bernoulli variables which are following the Bernoulli distribution with the same parameter P, then we say they are identical to Bernoulli distribution. So what we are talking is, we are talking about sum of such n independent and identical Bernoulli distributions. I am not putting the letter n, sum of n independent and ii. So we define x1, x2, x3, etc. xn, n independent and identical variables, and this independent and identical is abbreviated as IID. So let x1, x2, x3, etc. xn be IID Bernoulli variables. The IID Bernoulli variables. What's the meaning of IID Bernoulli variable? As said, the trials are independent. Trials are independent. So first experiment and second experiment, the result of the event, they are all independent. So x1 value is not dependent on x2, x2 value is not dependent on x1 or any of these values. So the value of x3 is not dependent on any of this. So any xi value is not dependent on any xj in these selected n variables. We say they are independent and they are identical. Identical in the sense you have every xi following the Bernoulli distribution with same parameter p. So every xi follows same Bernoulli p and are independent. So this is the meaning of IID distribution. And now we are talking about the sum of that. So sum of your x1, x2, etc. xn now can be written as x1 plus x2 plus x3 plus etc. plus x. Now we see what happens to sum of these particular n variables. So let us take each of these variables. So since x1 is a Bernoulli variable with p, so you can have the distribution of x1 as 0, 1 with probability of x is equal to x1 with q and p. Because the distribution is identical, probability is same, q and p. Now x2, if you write distribution of x2, it is also taking values 0 and 1 with the same probability, say q as well as p. Now if you look into x1 plus x2, now you could have various combinations here. So you will have x1 taking 0 and 1, x2 taking 0 and 2. So if I say my x1 is just equal to 0, 1, in that case x1 plus x2 will be same as 0 as well as 1. If your x1 is taking the value 1, then x1 plus x2 will be 1 plus 0 and 1 plus 1, which is equal to 2. So if you look into all possibilities, x1 plus x2 is taking three values here, which are 0.